Good evening. I would like to introduce Markin and Bushing, who are here to talk about Wii hacking. Last year, Bushing was here talking about Wii hacking, and 1 year later, this is the progress they've made. So if you'd like to give them a round of applause, please.
Thank you. As you may have heard, I am Bushing. I was actually here last year. I made a brief 5-minute presentation about the Wii. It was on no sleep after about 48 hours, and we had just managed to get unsigned code running for the very first time about an hour prior to the presentation. So since then, we've actually gone through and explored further, made some releases, and we're going to talk about that. So here is our presentation. All right. Talking about the Wii. Oops. So discussing the Wii, one of the interesting things about the Wii is that it is sold better than all of its competitors. I think most recently I checked and they had sold about 40 million of them, which is about as many as the Xbox 360 and the PS3 combined. Part of that is because it's pretty cheap. It's only about $250. Nintendo is very rare in that at that price point, they are actually making a profit on every unit sold, whereas I know Sony loses some amount of money every time you buy a PS3. They just hope you'll buy enough games that they'll actually make a profit in the end. The Wii is pretty portable. Hopefully we're going to have one up here in maybe 20 minutes or so to do a demo, but it's a small little box. Makes it easier when you have a pile of 3 or 4 of them. It doesn't take up the whole living room. One of the biggest things with the Wii is that it's backwards compatible with the GameCube, and this was very important because one of the biggest marketing weaknesses of the Wii has been its game selection. A lot of people felt that it doesn't have very many good games, especially at launch. So something that helped was that it was already able to play every single GameCube game flawlessly right out of the box, and we'll talk a little bit about that later, why. They also tried to make it a very modern console and wanted to make it sort of a media-ish, newish console, and so they added built-in support for all the ways that you might want to connect things to it in your home. So we have Wi-Fi and Bluetooth, and you can use SD cards. It has a little photo viewer and an MP3 player, etc. One of the most unique features of this thing is something that Nintendo refers to as Wii Connect 24. And they're very vague on this point. They just sort of mention that it has something to do with online gameplay, and it's why your Wii light is orange instead of red when you turn it off, and yeah, some stuff. We'll talk about it a bit. As far as the actual hardware design goes, it is basically an overclocked GameCube in many ways. They use a similar processor, which is a custom processor from IBM, a version of the PowerPC that they codenamed Broadway. Runs at about twice the clock rate of the chip that was in the GameCube. It also uses a custom graphics processing chip called Hollywood from ATI. Again, it's similar to the one that was in GameCube, the Flipper, but about twice the speed. It has a pretty small amount of memory compared to the other consoles, but the memory it has is very fast. Also, they very aggressively manage the memory in each game, so it actually works out. The device came with the standard I/O ports that a GameCube had, meaning 4 controller ports and a couple of slots for proprietary memory cards. It only has 480p video output, which is, I think, worse than its competitors, but it's enough to power most consumer TVs. You know, it looks good enough for the market it's intended for. Also, it will work on standard definition TVs, which is a pretty big deal if you're trying to move units. As mentioned, it has a collection of ports. It has a built-in 0.5 GB NAND flash, which is what it boots off of, and it lets you download and buy games from Nintendo and then save them onto the console, as opposed to just having to insert discs every time. It marks a big departure from, say, the GameCube, because it means that the unit doesn't actually just turn on when you put the disc in. You turn the unit on and it starts running stuff, and then maybe you put a disc in, or maybe you go play a virtual console game. Maybe you run your Homebrew channel, etc. The drive that it uses is basically a DVD drive. It won't read DVDs, or at least it shouldn't. It's looking for a slightly modified DVD format that Nintendo created up with basically just to try to frustrate people trying to rip the discs. So if you take a normal Wii or GameCube disc and put it into your PC and you try to rip it, in general, it won't recognize it. And that's mainly just obfuscation. And they have this security subsystem, which is why it took about a year of hacking for people to actually be able to run any code on it. Let's see. As far as architecture goes, as I mentioned, they have two processors in this thing. They have the PowerPC, which is really what we thought of as the processor. This is what the games run on. It's pretty cheap and it's pretty off the shelf, but they run it at a very raw level. There's no hypervisor, no operating system or anything, so you're just running raw code on the thing. So there's no place for them to put any kind of security management on that. Also, the thing runs GameCube games, and there was no security then, so there's not really a whole lot they can do. And they came up with a very clever solution, which it took us a while to discover, which was that the graphics chip is actually also a I/O bridge, which is actually a full-fledged NEC ARM system on a chip. A nice chip decapping photo here, courtesy of our friends at FlyLogic. Unfortunately, this chip is, the features on the chip are so small and the chip is such a large area that it's, even with these high-tech tools, it's really pretty hard to get any information out of this. So all the information we're presenting here was gained just simply through disassembling software, and we weren't able to actually do some things like Karsten Knoll did with actually analyzing logic at an optical level. As mentioned, it's a system on a chip that we nicknamed Starlet because it's a little part of Hollywood. It runs a custom microkernel operating system written by Broadon. We'll talk about who Broadon is a little bit later. But it is all custom, which is interesting. So we were not able to leverage holes we might have found in UC Linux or any of the other standard embedded systems. Let's see. As mentioned,
Okay, it's the Starlet iOS basically verifies all code on the unit, or at least all code you would normally boot. So it verifies itself when you change to a different version. It verifies the games themselves. It verifies downloadable content and the system menu. So the entire boot chain is basically meant to be signed and authenticated. And well, it's really hard to run custom code because you can't directly boot anything through any normal mechanism. Oops. Okay. And yeah, and iOS is actually abstracted out. Developers don't even know what iOS is. If you ask Wii developer, they probably don't know, or they might know because they saw this stuff by us now, but they usually don't know. It's all abstracted out through API, so you just run a call and it gives you support for network or USB, and they don't actually say, oh, here's another CPU. They call it an I/O bridge, which doesn't really mean anything, and they just leave it at that. So it's really secret, to put it that way.
It really did work. They kept the existence of this entire processor a secret for a year and a half, which made it much harder to hack.
Okay, so the boot process starts, most of the code is booted from a NAND flash, but the boot process actually starts from a small ROM inside the unit. It's inside Hollywood, and it's really hard to get to. We've only been able to dump it pretty much by chance because we got there, but it's a small 1.5K bootloader that just verifies second stage bootloader from NAND, and it's very interesting because the second stage bootloader is actually hashed in SHA-1, and then that hash is stored in a one-time programmable memory area. So they make the Wii, they burn boot 1, and then they burn a hash into a little part of Hollywood which says you can never ever use a different boot 1 on this Wii. So they can change boot 1 at the factory, but once the Wii comes out of the factory, it's forever fixed, and they can never change it, updates or anything else. So boot 1 is actually a little more code, and it has RSA in it. So boot 2 is the main loader. It's kind of an iOS, but stripped down, no drivers. And boot 1 loads it and verifies it using real public key crypto techniques. Then boot 2, which is still a special piece of code in the NAND, then boots iOS. Oops. What the? Okay, that's what happens when you have too many buttons.
The joys of using our wonderful JavaScript-based slide package. So as Martin was saying, we have a three-stage boot process. This boot 0 that runs inside the ROM chip. This boot 1, which they can change, but only while it's in the factory. And then this boot 2, which is a fairly full-fledged bootloader that knows how to read files and run them.
Yeah, I'm just like way too nervous to hit buttons right. Okay, so iOS runs from NAND. It's actually in a file system. So boot 1 and boot 2 are special little reserved areas. iOS is resident in a little file system. So it's actually, there are several of them actually. And iOS is the main software for the startup. So when you're running games, when you're in the menu, it's iOS that's sitting there. And till now, the PowerPC is dead. There's absolutely no code running on the PowerPC. It's not even powered up. It's the startup controls the PowerPC. So it's kind of like a hypervisor in that it has control over what the PowerPC can do, and it can kind of peek at what it's doing, but PowerPC mostly has free reign, but iOS boots it up. So then the first thing that you see on a real Wii is the system menu, which is the little channel screen that pops up. That's PowerPC code that runs while iOS is running on the ARM. Boot 2 iOS menu, all signed using RSA, so it's all signed code. Since we can't change boot 1 either, the whole entire chain from boot 0 is signed. The reason for the whole boot 1 interlude thing that has the hash is so that they can update the security code, which is starts at boot 1, all the signature stuff, without making a new batch of chips. Like Microsoft with the Xbox, back in the Xbox days, had some bugs in their ROM. And the way they had to fix them was to actually trash a whole bunch of chips that had them. That's really expensive. So what Nintendo did is, let's put a really simple thing we can verify in ROM, and then put something more complicated in Flash, but make sure they can't change it ever, which makes boot 0 simple. So by doing that, they've actually been able to change boot 1 without touching it all, boot 0. So on the Wii, all software, which means channels, which is the little stuff on the Wii menu, games, disks, WiiWare, which is also channels that you can download, system software, they're all called titles. It's a unified signature and a packaging system. So they're identified by a title ID, which is just a little number. And titles are basically composed of basically three big important parts. They have the TMD, which is the title metadata, and that signs and describes the contents. So it's got things like the group ID, and that defines its permissions, and it's got the hashes of all the contents. So if you can verify the TMD, then it gives you an ability to verify the actual contents of the title. And the e-ticket is the license to the title. It's your decryption key for the title, basically. You've got common e-tickets, and you've got private e-tickets. So what they do is they can give you free tickets for system software, and then actually make you pay for tickets for downloadable content. It's got the AES key that decrypts the actual contents of the title, which is the data files and executable. And the master key for that, which is just encrypted, is stored in the one-time programmable area that we talked about. It's really hard to get to that because it's buried in the Hollywood. The tickets can also contain time limits. So you could have like a demo. You don't think they haven't used this yet, but they can use it. Signatures are RSA 2048, so it's really like impossible to hack because it's modern crypto algorithms that are not broken yet.
And one thing I would interject is that this is another cost-saving measure. They're actually able to distribute all of the software using Akamai or other content distribution networks, because anybody in the world can go download the entire library of Nintendo's Virtual Console games, but they're all encrypted. So the only way you can actually play them is if you buy a ticket which has your key from Nintendo.
As I said, the games are also titles, but they're on DVDs, which have their own protections for anti-piracy. It's a DVD, kind of, not really. It has some tweaks they made to make it incompatible with DVDs. So it's got physical protections on it that are really out of the scope of this talk, but they're using special manufacturing equipment to do them. The disks themselves have data. Ignoring the tweaks, it's basically an ISO. It has several partitions. It's a special format. Those partitions are encrypted using AES, and they've got the ticket, key, and they've got a TMD. Each partition is basically a title. It's a title turned into a huge block of data on the disk. Now, this is really interesting because you can't verify as 4 gigs of a game when you boot it. That's impossible. It would take forever. So what they do instead is they have a hash tree, which means each sector is signed. Then they put those sectors in a list. They put those in a big block. Then they sign those blocks, put them in a list. There's a little tree such that you can read a sector, read the signatures for that sector, and then you can verify those signatures at the read time. So they actually sign every single piece of data in a game. You can't change anything at all without breaking the signature, and it's still efficient because it's accelerated in the hardware. So it's really interesting. Like, most other consoles don't do this. The root of the signature is the TMD, which is, as we said, RSA signed, and the e-ticket has the key. So, why is this jumping? Somehow there's a there's a button that switches like 20 slides forward because I'm like that. Okay, moving on. Okay. The IOS, as we said, is a custom microkernel OS. It does most I/O, so it does all the peripherals that are connected to the Starlet go through IOS, and then Broadway can use it through an API. So there's an IPC interface that you can pipe commands between them. It even has a high-level network API, so you actually do BSD sockets over this interface. It's the entire TCP/IP stack is on the Starlet, which is pretty interesting because they can both use it at the same time. It does, of course, decryption and authentication, and it does the file system, which is on the NAND, which is kind of like Unix but cut down file system. It's got permissions. The users are title IDs. The groups are defined in the TMD, and IOS keeps track of what permissions the Broadway has. So each game can access its own save files and things like that, and they're all protected between each other. And Broadway can't see system files, which would be bad. It also controls the memory limits. It can steal some memory from Broadway and tell it to, you know, I'll keep this for myself and you can't touch it. It's got a modular architecture. The drivers are processes. It's like an operating system. It's got a system call interface internally, and so you have like a DVD driver and all that stuff. It's separate processes.
Microkernel architecture.
Yeah, it's a microkernel. So almost all the processes talk using standard system calls. The kernel itself runs from an SRAM that's built into the Starlet, but then the user space steals memory from the Broadway. That's so the 12 megs of MEM2, which is the 64 megs of RAM, are used for IOS, and everything else can't touch them. Well, actually, peripherals can touch them, but not the Broadway, so you can't modify anything there. So, I mean, this is a pretty secure system for the most part, but that's the theory. I mean, it's designed to be secure. The question is, can it be implemented securely? So I'm going to hand over to Bushing now.
The answer, of course, is no, not so much. So the way that we broke in was something that we called the Tweezer Jack, hence our name. As I mentioned before, the thing was from the beginning, this device was backwards compatible with a humongous library of GameCube games, which means they could make very few changes to add more security to it. So all that code's unsigned. The idea is that they just sandbox it, and so that you can't use any of the new Wii features. So for example, you could have a GameCube game, and it puts stuff on the screen. It can read your GameCube controller, but it's not going to be able to use your Wiimote. It's not going to be able to use the SD card or talk on the network. So, and it also runs at half the clock speed, which is what the original GameCube ran. Again, the DVD drive is actually pretty similar to the one the GameCube had, which was pretty funny because it meant that the mod chip makers were able to almost immediately just port over their existing GameCube piracy designs to work on the Wii. Some of you may remember TM Ink's slide that said, insert mod chip here. Well, it was a little bit harder than that, but not that much harder. So we were actually able to run some homebrew GameCube when we were using these chips, but it wasn't so interesting. It meant we could take something that would run on a GameCube and run it on a Wii, which doesn't really do much more than running on a GameCube. So you weren't able to access any of those features. And the way this is actually implemented is that the Wii always boots off of its NAND into this wonderful system menu, and then on the menu, you go to your little disk channel, and you put your GameCube disk in, and it says, oh, it's a GameCube disk. I'm going to reboot the PowerPC into GameCube sandbox mode. And the GameCube mode uses both of the memory banks we mentioned earlier. There's a main Mem1 area, which is 24 megabytes. Then there's an external chip that's 64 megabytes. And the GameCube only uses 16 megabytes of it as audio RAM. And the actual implementation of this is crucial for the next step. Tweezer Jack. So, although once you reboot into GameCube mode, you can read the lowest 1/4 of this external memory chip, this 16 megabytes of memory. You're not allowed to read the other because the Starlit iOS Hollywood contraption protects against that. You just get random garbage if you try to read it. However, I guess because of this, they didn't bother to think they needed to clear this memory area after rebooting. So, as I said, you start out in the system menu and it says, oh, you're a GameCube game, so I'm just going to reboot you into this mode. So they left all of their crap up there in the upper 48 megabytes. Normally you can't get to it. However, it is a chip. And so the chip has address lines like many chips do. And so if you go there and you start tweaking these lines and connecting them higher to low, you can actually change what it is that the Wii thinks it's seeing. With this, we were able to temporarily move around our little 16 megabyte window of memory throughout this entire 64 megabytes of memory. We were able to do this, and TMB Inc. did this, and he soldered up to his little GameCube controller port and bit-banged 64 megabytes of data. Oh boy, 64 megabytes of data out to...
It's the remote that has keys that just press all at the same time.
Should have used Keynote. TMB Inc. is the one that actually did this, and he soldered to his little controller port and bit-banged, painstakingly all the entire memory just out that little port. And we were able to go look through it and, oh wait, they're storing all the keys there in that memory, which was a huge mistake. I think they'd agree with me. So, as far as what we discovered when we found keys, it turns out that each console has some independent keys. And this is important because one of the early attacks that people had tried was they said, oh, well, you have this little NAND flash memory chip on a Wii. Well, maybe I want to buy some games and then want to give my friend, I want to give Mark and all of my VC wares I got. And so I'm just going to copy my chip and hand him a copy of my chip. And that just doesn't work. And the reason why is because there are several different keys that are stored inside the Hollywood and that you can't just copy that way. One of the interesting things that they did was they gave each console a private key using ECC, which is a little bit like RSA, and it's a public key system you can use for signing things. In order to verify that this is a legitimate key, there's a certificate that is signed by Nintendo saying, yes, this is a key that Nintendo made up, and it's not just made up by some program that Sega wrote on his computer. There's also a AES key that's used to encrypt the contents of the flash chip, and one that's also used to sign it in a certain way so that you can't just modify it with a chip of some sort. In addition to that, there's a common key, which is really the holy grail. It's what was the root of the encryption used to encrypt everything that the Wii had.
So if you have the common key, that means you can read every games and iOS's code, which is very nice because you can analyze it if you can read it. So once you have the common key, you can't change anything, but you can watch, which is very important.
There's also the SD key. In order to keep people from messing around with save files, they used a stupid little key to encrypt stuff on each little save file on an SD card. There's also a root certificate, which is how it does a chain of trust and verifies that the disk you've inserted really did come from Nintendo. And they actually got hip to us, and they tried to reclaim their platform by adding a new key for new Korean Wiis. So they added an additional special Korean key that is only there on Korean Wiis. So where did they actually keep these keys? Well, so they actually hard-coded some of them just inside the binary of the firmware. So you have your SD key, and you have your default common key. This is ridiculous because they actually went to the trouble of buying some expensive silicon to place their secret common key in a hidden spot on the chip, and then they just also happened to include it in all of their firmware images for no apparent reason. Again, this area where they're keeping these keys is this one-time programmable area we mentioned earlier. You have that common key. You also have your ECC private key and many other ones.
You might notice some resemblance here. Not sure why they went to the trouble of actually securing one key when they copied it to the binary. I mean, it's a default key that gets used when the other key is not available, but it's the same key. So yeah.
In theory, it only falls back on this key in the factory while it's still being manufactured before it actually gets the serial number assigned. They ran out of space, I guess, for some of these keys, so they added a third little chip inside the actual Hollywood package that stores some slightly less secure keys, but they're still important. So it has the certificate, which was issued by Nintendo and is part of the identity of this console. And also they ran out of room to store their new Korean key, so they actually stuffed it in there as well. All right, and there it is.
Looking at iOS, well, we said it's isolated, the user space processes can't talk to each other except for a defined interface. The kernel communicates with them through system calls, much like you would on a computer. So you could have a process access for the specific hardware that only it can access. You can do threat management, so it's actually multi-threaded and everything, and multitasking. And you can talk to other processes. The interface is very standard for a microkernel. It's using devices, so it's similar to Linux and Unix. You have /dev/something, and you can open, close, read, write, seek, and IO control, and a little tweak on IO control, which is called IO control V, which is a slight variation. So the devices are set under /dev. For example, ES, which is called e-ticket services, which does all the security stuff, has /dev/ES. DI, which is a drive, has /dev/DI. That's the DVD driver, and it does the hash tree and that stuff. There are many more. You've got USB, SD, network, blah, 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 blah. There are a ton of processes in iOS. Broadway can actually talk to iOS too. The way it does that is it gets marshaled through a little interface, and iOS has a process where everything from the Broadway seems to come from. So when you talk from the Broadway to iOS, everyone else on iOS thinks it's coming from a specific process inside iOS. So they can check for that, which is important. The signatures are all done by one function, which does RSA verification. Well, RSA signatures are done by one function. There's other algorithms in there. The function is called ESVerify_sign, well, main function. It uses a hardware SHA-1 engine, and it uses software RSA. So SHA-1 is accelerated, which is very nice because the disk needs to use it a lot. While RSA is just done in software, because it only happens a couple of times. So before loading code, iOS checks that SHA-1 hash and that RSA signature, and if it doesn't match, it just says no. Of course, the SHA-1 is signed by Nintendo, so they get ultimate control about what runs and what doesn't. iOS decrypts the RSA signature, it checks for the real signature, and if it matches, and if they're compared, then it verifies, and we can move on to load the code. For those of you who are not being exposed to crypto, you might think that RSA is some sort of really complicated, takes 1,000 lines of code thing. Well, the code's a little weird because it's big numbers, but you actually learn how to do RSA in high school. I mean, you only need to know how to do exponents and how to do mod, which is just a fancy way of saying take the remainder of a division. So it's big numbers, so there are peculiarities involved, but ultimately, it's really just you get the signature, you do it to the power of the public exponent, and you do mod the public modulus. That's really all there is to it as far as the decryption. A signature is really just the SHA-1 that's being signed, add some constant padding, and then that gets run through RSA, and you end up with the signature. When you decrypt it, you need to come up with the same thing. So you literally take those bytes that make the signature, take this one big binary number, run it through that formula, and then you get out the original signature, and you need to compare it with what you're actually being signed. So, Nintendo did RSA in an interesting way. They start off by doing the decryption, which is what you would normally do, it's all right, and then they ignore the padding. Now, that doesn't break the security, but it shows that they don't know what they're doing, which is interesting. And then you look at how they compare this SHA-1, which is only a bunch of bytes, only 14 bytes, or 20 bytes, and it looks interesting because, so they get the signature, and they compare it, and the compare function looks a little bit like comparing strings.
But these are binary numbers.
Yeah. For those of you who don't know, a C string compare function stops on the first null byte, which means if your signature has 00 in it anywhere, it stops comparing there. That's...
Fail.
Yeah.
Yeah.
Yeah. And they screwed up everywhere, all over the place. So I guess it's back to the NES days. This is 8-bit security here. So how do we abuse this? Well, there's a neat trick. I said it was an exponent and a modulus. Well, 0 to the power of anything, mod anything, is still 0. That's useful because we're stopping on a 0. That means our SHA1 needs to start with a 0. If we're comparing it to an SHA1 that's all zeros, because it's a string compare, it thinks it's an empty string. Brute force it, it's just a 0. So we can just tweak stuff, and so it happens to match a 0. And once it does, we can pass it as an original signature. We can use unsigned games, an unsigned system menu, unsigned ISS, and even an unsigned boot too. We can change all the code in the system using this bug. I have a little demo here, just to show how this works. I'm just going to type out some stuff here. And
so as you mentioned here, basically we have to do a little bit of fuzzing in order to manipulate this into something that satisfies our criteria where it needs to start with 0. And that means we have to try up to 256 times. So here we added the number 170 at the end to make it so that it worked out.
This was implemented in JavaScript, and it took 56 milliseconds. Not too hard. Get that? Yep.
All right. So what did we do with this? Well, we presented this, the Lego Star Wars exploit we demoed at 24C3 used this hack, but we wanted to come out with one that did not require a modified system to use. So we did the Twilight Hack. As a bit of background, the Wii stores most of its save files on its internal flash chip. So you run your game, you play Zelda, you say, all right, I want to save, and it just says, saving, don't turn off console. It's just saving to a flash chip inside of it. Then later, if you actually want to take a save file over to a friend's house, you have to exit the game and then go out to the menu, and the menu has a little data management thing where you can delete save games, copy them to SD card, back and forth, so on. One of the things they do is to prevent us from tampering with it, they use this private ECC key that is stored inside the Hollywood, and they use that to sign it. So the signature on this says, a real we signed it, and we didn't tamper with it. However, if we can actually extract that private key, we also can sign as that key. So in fact, all of our Twilight Hack were done using a program written by Seger and pretending to be TM Binks we. So now that we can do that, we can then modify save games, and this shouldn't really be a problem in and of itself. It's just data. However, programmers are often pretty lazy, and so we found a classic stack buffer overflow in Zelda, which is one of the very first games that they released, one of the most popular ones. Also one of the ones written by Nintendo, which we thought was good because that way Nintendo can't blame this on some sloppy third-party developer that didn't follow their rules. They didn't follow their own rules. So we just mashed the stack and then embedded a little loader inside of it that can go out to an SD card and then load an ELF file and run it. So here we're able to run Broadway code, which is again the PowerPC, which is still somewhat limited. Most games just run on it, but it doesn't give us the ability to go and say change the operating system or modify anything else like the menu. Here's a little bit of how we did it. Here, this is the Zelda save game loading screen. Here, you're supposed to see the name of Link, the main character, which here is XXXX and so on. You actually notice at the very end, it shows here a date here, which it shouldn't be. So it's showing that already it's getting very confused about what should be where in memory. So when you actually do, we did this, and then also we used the RSA verification hole that we had found to patch Zelda to re-enable all of the debugging features. All of the debugging features that they'd used for development, and so we were able to get crash dumps and exception logs, which were exceedingly helpful for figuring out where we needed to place our little register stores. So from there, we then made our little elf loader, and there we go. This was our first little release, a little proof of concept. So this is how you actually run this on your Wii. If you're going to go home tonight and download it and try it, if you have Zelda, you download these files we give you, and you put it on an SD card, and then you use the menu to copy it. There you go. You run Zelda. You can see our little Twilight Hack 0. We cleaned it up a bit so you don't have the ugly name. We figured out exactly what we need to write. Your character starts up on the screen, and you walk backwards. And there's your code execution right there. So normally the way this would work is that you would find a bug, and then you'd use the bug, and then the vendor would fix the bug. In this case, it's a bit hard because it's a game that already came out, so they can't take the DVD back from you and patch it and give you, say, here's a fixed DVD. So, this should be all right. And then, so they decided to try anyway. So they saw this exploit we released, and they said, okay, well, the data is getting there from the system menu, so we're just going to put a special check Zelda save file function inside the menu. And whenever you look, you try to copy this, that's what it does. We know what it does because they also left symbols in the system menu for us to find. So we have their function names too. Thanks, guys. So they try to do this, and then they botch it so that it's very easily deceived. So we just tweak our file a little bit and then make a new one, and then they really fix it, 6 months later or so. But then they botched it again, and so we just have to create a little bit more padding on a different file, and then we're still actually using the same exploit. We haven't bothered to find another game because we haven't needed to. This was the first game we actually tried, and we're still using it.
Okay, so we said that iOS boots from NAND. Well, it turns out that Nintendo decided that they wanted to upgrade this while maintaining backwards compatibility with games. And they felt that they needed to actually make little branches of iOS for each major update that they make. So what they actually do is they store several iOSs in NAND at the same time, and then each game tells you, well, I want this one to be used for this game. The system menu loads it for the game, then the game boots with that. This is okay because they're signed and everything, but when it reloads, it forgets everything because it's reloading the code and it doesn't store any state from the previous run. So the way they fix this is once it reloads, the system menu has to open the partition on the disk drive again, and then the iOS checks the TMD and the ticket and says, oh, I'm running this game, so I'm going to use these permissions.
So you're having the insecure processor give the credentials to the secure processor.
Well, the disk, it's also insecure,
right.
But yeah, basically. That's interesting, but the iOS still sets up the permissions, right? This is a private IO control, and the driver, DVD driver, sends these credentials to the ES driver. So it's, it's an internal thing that we're not supposed to know about. Except they don't check where it comes from. Remember when I said that PPC boot was where all the requests from the PPC came from? We can do this from PPC boot. We can tell iOS, hey, use these permissions. And it just uses them. So it's kind of like sudo, which is really interesting. You can just send the TMD and the ticket, which is not very secret, because you can send the TMD and the ticket, which from the system menu you can download from Nintendo's server. And then you get system menu permissions, just like that. But even more interestingly, group ID 0 happens to be the group ID of all the special system files. Those system files are also set as group readable and group writable. And we can set that group ID and the TMD, which is not used for anything normal, but it turns out that we can fake sign it, of course, because it's RSA signed. And then we have full access to everything in the NAND, including all executable code and anything else, and all tickets, and you can even copy like words using this from other consoles. It's all in NAND. It's like, give you root file system access. We call it ES identify instead of DI verify. This is a little more useful like that. They also, the Intel claims that we cannot play DVDs. That's a lie. The disk firmware rejects non-Wii disks because you can't read the disk, supposedly, but it turns out that they left in a DVD mode that you can turn on, and then you can read DVD disks. Because I guess they wanted to have DVD video support. iOS blocks these commands, they actually filter them out, except there's a bit in the TMD that you can turn on, and then it doesn't filter them out. That's very nice because we can play DVDs. We actually ported M-Player, and it's really cool. So the problem is that DVDs imply DVDRs, and DVDRs imply you can burn this, and you can burn this implies you can burn a game to this. And if you manage to get it to use these DVD calls for games, then you can Wars them, which some people eventually did. Before this happened, we tried to tell Nintendo. I'm going to let Bushing.
Yeah, so one of the things that some of our Xbox colleagues suggested was that Microsoft had actually, in the end, behaved pretty well when they were told about some security problems that they found while hacking the Xbox. I believe they actually ended up flying them out eventually and having them present. So we thought, well, maybe it would be fun to have a nice open relationship with Nintendo. At least say, hey, here's a bug that we actually don't really care about because we're not using it to run our code. We think it could be used for piracy, so we'll just tell them, and maybe they'll fix it, and maybe they'll appreciate the fact that we actually tried. Actually, what they did instead was they ignored my emails, so I posted on our blog, and then they started leaving me voicemails at work. They were very proud of themselves for figuring out my name and where I work. So, and the moral of the story is, don't bother.
It's up and down. Stupid things. Okay, I understand that you screwed up here, but how do you hit the wrong key here? Like, I blame you for this one.
So, as far as response goes, we demonstrated the first unsigned code back on 24C3. They then figured out what it was that we were exploiting, and then they kind of released a updated version, which was not actually used by anything, but it was still out there about 3 months later, I guess. It didn't do anything, but I think it was there to scare Datel, who was trying to release a commercial product that used it. They actually then, a few months later, released a version 3.3 that fixed it in more versions and also tried to do their little Twilight Hack check.
Yeah, they fixed it in the system menu iOS, which is important because you can't boot fake-signed games with this. But if you already can run code, you can still change to iOS, a different iOS, and still do it. So it's a partial fix. And that's why your hack was screwed up.
So they then, it took them a little while longer. Then a few months later, they actually then went and fixed it in all versions of the firmware, which has actually been fairly effective in combating virtual console piracy. But they also, at the same, about the same time, tried again to fix Twilight Hack and failed.
And that's where we're at right now.
So as far as going briefly over the problems of approach, what should they have done differently? Well, they took an RSA signature thing, which is something that's used all over the place, and there's plenty of public domain code just waiting for you to use it. And for some strange reason, they decided to rewrite it all themselves, and they messed it up. So there's a bug in this code which should have been easy.
Not those keys.
They also then went on to store all of their keys in external memory, which we could then play with because it's hardware. They then also forgot to clear these keys out when they were using them, when they were done using them. So we were able to use their legacy mode to actually get into this. And then the last biggest one, which is still there, is that they only check the signature when you install new software. So you can actually go and use a program like Starfall and go and modify the system menu once it's there all you want. And they never bother to actually check.
So if you have NAND access, either software or hardware with the keys, you can still do anything.
As far as API problems goes, they have this interaction between these two processors, but you're allowed to arbitrarily tweak this the iOS code.
Oh, sure. You can also call it private functions, like he has identified. It's kind of weird because, I mean, they tried to verify some of them, but they obviously didn't go through and said this one, yes, this one, this for this one, this one for this one. Some of them have checks and some of them don't. It's missing a code review here, or something like that. It's pretty poor. The caller checks and the parameter checks too. There's some things that aren't re-verified right. And the DVD code was just sitting there unused. They really should have taken that out at some point.
As far as procedure goes, just running through briefly, they had put ways in the software for them to download firmware updates and such over the internet, but it's taken them on average about 3 months from whenever they find a bug, fix it, and actually release it. We can read their build dates on their binaries and see this. Unwillingness to talk to security researchers. They left boot 1 unpatched for a year. If you recall, this is this thing where they can actually fix bugs in the factory before they release it without having to make new chips. They didn't use it for a whole entire year. We still don't know why. When they did fix bugs, they did a kind of a knee-jerk thing. They even went and spent a lot of effort to fix the original Tweezer attack, which is lame because it was something that had to be done once. So there's no reason for them to actually go back and fix it. I also think that part of the problem is that there's 2 different teams. There's most of the code for the PowerPC is written by some people in Japan, and all the code for the ARM chip is written by a company in California.
Hi, my name is Michael Style. I've done previous talks on console hacking the years before, you might remember me, and I asked these guys to have this one last slide. You might have even seen that slide before. I did this last year and also in other presentations, which is a little about hacking motivation. And those guys agree with me as well. I talked to the iPhone hackers, they agree with me as well about what is the motivation of hacking things. And I've put together this on this slide. This summarizes all the gaming consoles and other embedded systems that have security built in the last 7, 8 years or so. Up to, well, the latest one, the iPhone. And the security has been increasing, well, not on all the systems, but Xbox 360 and PS3 are pretty strong. The Wii not as strong. And, well, the stronger systems took longer to hack than the easier systems, obviously. But there's one that has not been hacked, which is the PlayStation 3. And all of them, except for the very early PlayStation 2, have been hacked by people who were interested in running Linux or running Homebrew software or in other ways opening the system for their own code, for their own hacks. Not for piracy, not for copying, not for breaking encryptions of TV or in case of the iPhone, it's also been Homebrew and using it internationally as opposed to avoiding contracts. But the effect of all these things was that you could always do all these negative things, which was very negative for the vendor, like pay-TV decoding, piracy. So what they should have learned out of this is that you should always have separate security systems, one that protects your system against piracy, but does not necessarily lock out people from running their homebrew code. So they could do that. There are ways to do that. And on the PlayStation, it was done correctly. They have this hypervisor that you can run Linux on. They even do their own Linux distribution for it, or they maintain their own Linux patches. And you can use Linux, or you could port your own operating system to the PS3. That is fine, and still the security system of the PS3 is strong and it works, and there's no hack there yet. So I think this slide pretty much proves that everything has been hacked, but the one that is the most open one.
Yeah.
I'm just going to apologize for a second for the technical problems. We're using S5, which is a really cool HTML-based presenting system. But yeah, I'm just saying, the screw-ups were not knowing what button to push on both of our sides, not the system. It's just yeah.
Demo.
So moving on, I'm going to try to do a demo here. This is 640 by 480, so I don't know how it's going to work out, but we're going to try it. Hopefully. Okay. So first, I'm just going to show the usual current homebrew state that we have right now. You turn on the Wii, which is mostly a normal Wii right now. And if this works, yes, it does. And now my remote doesn't work because it hates me. It's not turning on. Great. Anyway.
It'll time out.
Yeah. I need a timeout, but yeah, batteries might help. Yeah, batteries. What? Because I need to join the Homebrew channel. Not for the Homebrew channel, then. They go in order.
Doesn't matter, just do it. Thank you.
Anyway.
Thank you.
So we have this little channel that I'm going to show you later, but we're working on, this is all using Nintendo stuff. This is using iOS, this is using their, we have our own APIs, but it's using the same system. It's written like a game. The main issue with that is you can't run your own code everywhere, like the startup. So what we're doing is we're actually replacing boot 2. Okay, there we go. So this is our current Homebrew state. So this is our system menu. And what we have here is the Homebrew channel. No sound, but oh well.
We wrote this.
Yep.
Yeah.
It took a while, but yeah. And you run it, and it boots your applications from the SD card. You can even run Linux on it. Like, this is really old build, but we'll just show a login screen or something. Maybe this, there you go. Just some random stuff. The issue with these is that this Linux is actually still running under iOS. It's running on the PowerPC only, kind of proxying through iOS, but it's very limited. No network, USB's kind of dodgy, all that stuff. So we wanted to improve on this, and we're working on replacing all of the code as soon as we can in the boot sequence with our own code. What we came up with is with replacing boot 2, which is the first bootloader that we can touch. And that's what I'm going to show you right now. This is custom code, as much custom code as ever possible on the Wii. You can't get any better than this. It's actually, I have a little LCD screen, some debugging stuff in here, and it should boot. Maybe, possibly. We just screwed up the video mode, so I'm not sure this is going to work. So just press A. Yeah, it should go either the system menu or the Homebrew channel. We did this about, while the talk was already going on, it was finished, so apparently we have some issues, but you can go down to the Hack Center and watch it work there, because we're doing really ugly things to get this to work right now here.
The point of this, though, is the only, we shouldn't be able to do this. The only reason that we were able to do this at all is that they've neglected to patch this boot 1, the thing that their little rescue plan for the factory, they've neglected it for a year. So we can still do this on 30 million Wii's at least.
Yeah. They fixed it in Korea for at least for some or all Korean Wii's, but.
So we have some time, a brief few minutes for any questions.
From the audience?
Hi. Your colleague asked for the manufacturers to keep the devices open so that you can run Homebrew software, but I don't think that's very realistic, because as you stated at the beginning, with selling the items, they actually lose money, and if you would buy it and they lose money and then run your Homebrew software, I don't expect
the way that Sony handled this, so the question was that why should manufacturers let you run your own code if it's code you wrote and that means you don't buy games? The way that Sony handled was you can use almost all the PS3 hardware, but they restricted just enough so that you can't really run a nice game with it. There you go.
Yeah. Hold a second. I was neglecting to show the debug upload, which was holding up that thing. There we go.
Yay, boot me.
Probably video thing. Or something. Yeah, there we go. So that's actually picking which thing to boot without even iOS running. It's totally custom code at that stage, and then it bootstraps iOS.
Just very quickly, can people wait till the Q&A's over before you escape? There's quite a lot of people waiting outside trying to rush in, so.
Next question then, maybe?
Another question?
You said that first BIOS is runtime programmable. Would it be theoretically possible to clear additional bits to 0 to alter the code from the bootloader 1?
It's possible. We haven't actually figured out how they're locking against it, but even so, we did the math, and that wouldn't reduce the complexity of finding a collision enough for us to really actually use it.
Hi.
People, can you please be quiet if you're going to actually leave?
So you've managed to dig a few keys out of the console. So my next question is, I would really like some RSS feeds in my newsreader because the newsreader of the Wii is actually really cool. So could you please, for maybe next year, add some RSS feeds to the channel?
We'll look into it. Yeah.
Actually, I know how to use stuff. It has its own RSA signature, which might actually be a real RSA implementation. So you might have an issue there. That's re-implemented in the PowerPC. But it might be wrong too. We don't know.
It seems like Nintendo invested a lot of effort in preventing unsigned codes, but it seems like they didn't do a lot against the simple DVD drive attacks.
Yeah.
Why is that?
The drive is outsourced. So it's kind of out of our hands. They just, the commit sheet that does the drive, they ported it over from the GameCube to the Wii, added dual layer, a couple of things. But apparently they are neglected to fix the mod chip issue. Now they're doing lots of stuff to try to stop them. They actually, on the latest revision, combined the CPU and chipset onto one big chip, which is currently impossible to hack. But Nintendo didn't do this. It's Machida. So I guess it's the company split that.
Well, it's that, and I think it's at least 2 or 3 orders of more magnitude, more expensive to fix hardware than to fix software.
That too.
That's really what it comes down to.
Got time for 1 or 2 more questions?
What was that? Release date of Boot Me.
No release date. We don't
When
give
it's
out
done.
release dates. Yeah, when done. That's the release date.
Okay, if there's no more questions, I'd like to thank the 2 speakers again.
Thank you.